Hello everyone, welcome to our TESOL Global YouTube channel. This is our FPGA video series where we will explain different aspects of FPGA. We'll provide different examples and demonstrate some projects. In this video, we will continue explaining basics of Verilog coding, and at the end we will show an example Verilog code. This is the fourth part and last part of Verilog basics. I'll suggest you to first check other three videos if you came to our channel for the first time. From the next video, we'll look at the basics of VHDLs as we received a lot of requests for VHDL basics. In the second part of Introduction to Verilog video, we talked about the procedural assignment. In this video, we will put more light to it. So procedural assignment is part of behavioral description. Generally, procedural block has a region of code which consists of sequential statements which are expected to be executed one by one and also in an order that they are written. This is similar to high-level programming language like C. So this is basically the case of software implementation, but in hardware implementations, things can operate parallelly. There are two types of procedural block. One is always block, which is a continuous loop that never terminates. This is synthesizable and used in the body of Verilog codes. And then we have initial block. It is executed once in the beginning of a Verilog test bench. So this is basically being used in the simulation and it is not synthesizable. So now we'll look at always block. So here you can see a basic syntax of always block. So in always block, it is start with always at and there is a triggering condition. So after that, you have the block of statements. So whenever there is the triggering condition, the always block executes. So it is like an infinite loop. So the block statements, it includes the logic and this block statements can be either parallel or sequential. So whenever the triggering condition appears, the block statements inside always block gets executed once. And these things keep happening like an infinite loop. So it means like whenever the triggering condition will appear, the always block will be executed. Now, inside always block, reg or reg is the main variable being used. So the reasons are always block executes event when the event expression triggers, otherwise it holds the previous state data. Therefore, it requires an arrangement to remember the last value assigned. So only reg type variables are appropriate within always block. The reason for this is the reg can hold the data. Of course, other variables like where can appear in the event expression. Now we'll talk about initial block and its use in the test bench. We talked about the test bench multiple times in our previous videos briefly. Today we'll see the basic structure of a test bench. So test bench is a Verilog program or a program which is not synthesizable, and the main purpose of the test bench is to check if the main Verilog code developed for an application is working as expected or not. So here you can see the basic syntax of the test bench. So for test bench, we can start it by defining the time scale. It includes unit time and the time resolution. So the unit time is the measurement of per unit delays in simulation, for example 1 nanosecond. And the time resolution represents how delay values are rounded before being used in simulation, for example 1 picosecond. So if you do not define the time scale at the start of a test bench, then your default time will be in picosecond for Modelsim simulation. So now the next line is module, and you write the name of the test bench. So unlike Verilog module test bench, module has no inputs or outputs. Then we write the variables which will represent mainly input or output. Then there is the design instantiation, which is mainly mapping the test bench inputs and outputs to main Verilog code inputs and output. Now we will write our main test bench logic inside initial block. So any code inside initial block is executed once and it is not synthesizable. And here you can also see a timestamp which is 10 nanosecond here because we define the unit time as 1 nanosecond at start. So the main test bench code goes within the initial block. Now moving into some other important assignments of procedural blocks. So there are mainly two types of assignments that can take place within the procedural blocks, which are always and initial blocks. So one can be the blocking assignment and another is the non-blocking assignment. So the blocking assignment statements are assigned using equal sign and are executed one after other or sequentially, which is similar to a microcontroller code execution, or this is kind of sequential code execution. And we have the non-blocking assignment. So the non-blocking assignment statements are assigned using less than equal sign, and it's scheduled without blocking the execution of following statements, which means it can execute codes parallelly. So the blocking assignments, they can mainly execute the codes sequentially, and the non-blocking assignments can execute the codes parallelly. Now, as always, we'll look through an example. First, we'll simulate it in Modelsim, and then we'll implement it in Quartus Prime. And finally, we'll upload the code in MaxChan Development Kit. We selected a 4-bit ring counter for this video as an example. A ring counter is typical application of the shift register. The only change with the shift register is that the output of the last flip-flop is connected to the input of the first flip-flop in the case of the ring counter. Here you can see the logic circuit of a ring counter. Also, we have an example timing diagram of the ring counter where each bit is shifting one place with each clock cycle. And the last bit moves to the first bit again at the end of its final bit number. This process continues with the clock cycle. And here you can see the Verilog code for the ring counter. So in the Verilog code, is showing in each clock cycle the output is shifting it bits one place by implementing the for loop. Now we'll move to the Modelsim and Quartus Prime. Before going ahead, we'd like to ask you to subscribe the channel if you are benefited from our content. Also, click the ring bell to get notification whenever our new video will be released. It just shows more than 50% of our viewers didn't subscribe to our channel. So please subscribe and help us to grow our channel so that we can provide much more quality contents. So now you can see the Modelsim window. We have already wrote this code. Here you can see the code, and we already have prepared the test bench. So here is the test bench. So in the Verilog code, at first is mainly defining the input and output, and then here you can see we have a for loop. This for loop is being executed in each clock cycle, and this mainly shifting the output one space so that the ring counting can happen. And to start the code, first you have to reset it so that the counter has some value to start with. Otherwise, there will be no value for the ring counter to start the counting. Now for the test bench, here you can see we didn't define the time. It means whatever time we'll write here will mainly be in picosecond. So again, we define the input and output. Then we mapped the test bench input and output with the main Verilog file. And then here you can see it says 10, which is means it's a 10 picosecond. So in every 10 picosecond, the clock cycle is changing. And then within the initial block, we are writing the main test bench code. So first we will reset the counter so that the counter will have a number to start the ring counting. So if we move to the simulation, now we will add the signals to the waveform. So now if we run the simulation, let us run it for a few times, but we cannot run it for more than 15 times because this is defined in the test bench. So if we zoom it, you can see here when we reset the counter, then it gets a value of 0001, which is the start of the counter. Then after the reset is completed, with every clock cycle, the 1 is shifting. So here you can see with each clock cycle, the 1 is shifting its place to the next place, and it will continue this with the clock cycle. So now we'll move to the Quartus Prime. So in the Quartus Prime, we'll mainly synthesize the code and we'll upload the code to the MaxGen Development Kit. So we'll just demonstrate the ring counter in practical. Now we will synthesize the code in the Quartus Prime. So here you can see the Quartus Prime window. Again, we already have written the code for the Quartus Prime, and here you can see a bit of difference than our Verilog code in Modelsim. So it's similar to our previous examples. For example, in the previously we demonstrated the counter, and we added an extra part for the counter so that you can see the counting. Because here we'll use 50 megahertz clock cycle, so we'll divide the clock with a number so that the clock will represent in a way which can be visible to your eye. So here this part is mainly is the clock divider, which will divide the clock for 1 second. So rest of it is similar. So you can also see the hardware in the sub window. Here the hardware is also a bit different. In our previous videos, we mainly used the LEDs on board. So for example, we used these LEDs, but we discussed this LEDs has some issue. It's not an issue, but like these are mainly in connected and active low, which means whenever you are giving high signal or whenever you are asking it to turn on, is mainly turning off. So to solve that, we use an inverter. Rather than using these LEDs, today we'll use another kind of connector which is within the MaxGen development board, which is mainly PMOD connector. So it has two PMOD connectors. We'll use one of the PMOD connectors today to connect the LEDs in this breadboard, and these LEDs will mainly show the output. So if we go to the pin assignment, you can see here, if we go to the pin planner, we already connected the pins. So these output pins, these four pins are mainly the pin for the PMOD connector, which is this connector. As I said, it has two PMOD connectors, so we are using the first connector here, and then we are using one reset switch, which is this switch. So the two application of this switch, first of all, we have to press this switch when we start the codes. Otherwise, the counter will not know from where to start, and it will just stuck into some random value. So we have to press these counters to guide the ring counter to start mainly is counting. And then you can also press this switch to reset the counter from start. And we are using this pin AM9, which is mainly the 50 megahertz clock. So we're using 50 megahertz clock, and we're dividing it in a way so that the ring counter will change its state in every 1 second. So now if we go to the code and if we just synthesize it, so now it's synthesizing. As we discussed in our previous videos, it takes a while to complete the process. So now the process is completed. So now the synthesizing is done. Let us turn on the board. So now we'll open the programmer. We already selected the Max 10 Development Kit chip, like when we configured Quartus Prime. So now we'll select the file, which is the SOF file. We'll click this and we'll click start. So the program is done, but here you can see none of the LEDs are on. Only this LED is on, but is connected with different pin. So to start the ring counter, as I mentioned, first you have to reset it. So when we done the reset, you can see the ring counter is now working. So here it is not connected. Let me connect it. Now you can see it's working properly. So again, to reset the counter, if we press this button, then the counter will reset and it will start from its initial state, which is defined in the code. And you can see the change of states are happening in 1 second. It means like in per second is just changing the state, because we are using the 50 megahertz clock and we are dividing it in a way so that it can does this 1 second state change. So this is the end of our demonstration. So this is the end of this video. You can download this Verilog course from our TESOL Global website. The link is given in the description. In our next video, we start looking at the basics of VHDL coding with some example codes. We received multiple requests to make some videos on VHDL. Please subscribe to our channel for more videos like this. We'd like to thank those who already subscribed and helping us to grow our channel. Add likes and comments and give us suggestion of what kind of video you want us to make. Follow us on LinkedIn, Twitter or X and Facebook. Thank you for watching. See you next time.